This is our, I think we decided, fourth one being back in person, so we're glad that you all are here. How many of you have ever been to Astronomy on Tap before? Okay. How many is it your first time at Astronomy on Tap? Wow, awesome. Welcome, everyone.
How many of you have listened to Astronomy on Tap on streaming online?
All right.
All right, thank you, guys. Well, we're trying to get the streaming right now, so that people can follow it online.
Hi, everyone online. We hope you're raising your hands as we ask these questions as well. Oh, you're up there. Hi.
Yeah, the camera is right here, so say hi.
Okay, so how many of you knew that there's a bunch of space research that happens right here in San Antonio? How many of you, if you work at the Southwest Research Institute or UTSA, put your hands down? Now we're going to ask the question again. How many of you knew that we do a lot of really cool space science research out here? Okay, not too many, so that's good. Well, we're very excited to share some of that with you. First, we're going to tell you a little bit about what we are and who we are. We are Astronomy on Tap.
All right, yeah, Astronomy on Tap started in 2013 in the region of New York by a postdoc, what we were some years ago. And it was a way to bring scientists in the bar and have, explain what the research we're doing and in a very friendly environment. And all those evenings included trivia where you could win some prizes. And so we decided to bring that in 2017 in San Antonio. And we were the second location in Texas after Austin. And now we actually, Austin kind of retired, I guess. They're not running it anymore.
So then we are the best location in all of Texas.
Woohoo!
Cheers.
Or maybe they're very, very careful with COVID also. It's another option. Feel free to wear your mask if you feel like it. We'll try to be careful. Michael, what do we have tonight?
Thank you. Well, tonight we have, as usual, our two speakers, and then in the middle our Astronomy in the News. So our first speaker is Dr. Rohini Giles, who will be presenting Sprites, Elves and Shooting Stars, Unexpected Observations from the Juno Mission to Jupiter. And then Caleb Gemar will give our Astronomy in the News in the intermission. And then yours truly will present on stellar occultations. What are they and why are they important? So.
And tonight we have some special prizes to win in the trivia that was given to us. Actually, thank you, Robert. This is a 2022 Night Sky Almanac. So the three first people, the three first winner will actually win one of them. So.
And a few cool posters too. Some I lugged all the way from Montreal at a conference, so
Thank you.
They're Canadian.
Thank you, Michael. So yeah, we have posters, we have almanacs, we have a beer cup also to win, and the questions will be about Jupiter and Venus, right? That's the questions.
A mix, yeah.
Yeah, there's a mix.
As usual.
What else? Oh yeah, at any moment during the talks, if you have any questions, text to this number. We'll receive the question, and at the end, there's a Q&A with the speaker. And the keyword. What is the keyword?
We'll do that when we bring it up.
Okay. Can you explain what's the keyword? Okay.
Okay. So with that, let's go ahead and you can also, hashtag AOT, SATX if you're on social media. And we are excited to bring up our first speaker, Dr. Rohini Giles from the Southwest Research Institute. Let's hear it for Rohini. Dr. Giles graduated from Oxford University with a PhD in planetary science in 2016. After a couple of years at NASA's Jet Propulsion Laboratory in California, she made the right decision and moved to San Antonio in 2019 to continue her research into planetary atmospheres at the Southwest Research Institute. In her previous work, she has focused on studying the composition and cloud structure of Jupiter's atmosphere using infrared observations. But at SWIRI, she is also branching out into other planets, Venus, and other wavelengths like the ultraviolet. So we are going to hear an awesome talk from her called Sprites, Elves and Shooting Stars, Unexpected Observations from the Juno Mission to Jupiter. And before we hear the round of applause, we need the drinking keyword from Rohini.
Which is spin.
Spin. So for those of you who are new here, what we do when Rohini says spin, we say, woo! And you take a sip. And Astronomy on Tap is legally not responsible for how much you drink. So if you are drinking a lot, please Uber home or get a ride. And with that, we're going to get her presentation open. And let's hear it for Rohini, everyone.
So those of you who are not regulars at Astronomy on Tap may not know that Southwest Research Institute, or SWRI, which is here in San Antonio, is actually the lead institute for several big NASA missions. And tonight I'm going to be talking about one of those, the Juno mission to Jupiter, and some of the unexpected observations that we have made. So Juno has been in orbit around Jupiter since 2016. It's in a highly elliptical polar orbit, so most of the time it's actually quite far away from the planet, but every 43 days it gets in really close, and that's where the vast majority of our science observations happen. It comes in over the North Pole, goes past the equator, and then departs Jupiter under the South Pole. And that gives us a really unique view of Jupiter's polar regions, which can't be seen that well from the Earth. These are all the different science instruments that are on the Juno mission. So I mentioned before that SWRI is the lead institute for the whole mission, but in addition to that, we actually built a couple of these instruments here in the lab in San Antonio. And one of those is the instrument that I work on, UVS, the ultraviolet spectrograph, which records light from the far ultraviolet part of the electromagnetic spectrum. Juno is actually a spin-stabilized so as it's orbiting around Jupiter, it's also spinning on its own axis once every 30 seconds. And UVS is sitting there looking out the side of the spacecraft. And so every time Juno spins, UVS observes a swath of the planet. And when we stick together lots of those different swaths, we can build up these really beautiful ultraviolet images of Jupiter. And here in blue is one of those ultraviolet images. So we're looking down at Jupiter's north pole, and the ultraviolet light is showing us Jupiter's northern aurora, which is the equivalent to the northern lights on Earth. So Jupiter's aurora form the same way as the Earth's. The planet's magnetic field causes charged particles to accelerate along magnetic field lines towards the pole. And then when they hit the atoms and molecules in the upper atmosphere, they cause light to be emitted. For Earth, it's mostly nitrogen emission, but Jupiter's atmosphere is mostly made of hydrogen. So for Jupiter, the auroral emission is mostly hydrogen emission. And hydrogen emission is mostly in the ultraviolet, or it's extra bright in the ultraviolet. So the ultraviolet spectrograph was specifically designed to study Jupiter's auroras. But as beautiful as the auroras are, we knew that we were going to see them. And I promised a talk about unexpected observations. So without further ado, here is data from a single spin of Juno. So I mentioned before that Juno spins every 30 seconds, and each time UVS observes a swath of the planet. So that's what you're seeing here. And the kind of circle around the pole is Jupiter's southern aurora, the southern lights on Earth. And then to the top left, you're seeing a little bit of extra blue region, and that's actually reflected sunlight. So that's the side of the planet that's facing the sun, and you're seeing a little bit of reflected ultraviolet sunlight. But what stood out to one of my colleagues as he was flicking through the data spin by spin was a little bright flash that I'm highlighting here. So it's pretty far away from the aurora, so it's not part of that, but it's a lot brighter than the surrounding reflected sunlight. And it was only present in one spin. Not the previous one 30 seconds earlier, or the following one 30 seconds later. So we just happened to notice this one by chance. We don't normally look at the data individually like that. So we decided we would systematically filter through all of the observations from the whole mission to see if we'd seen anything like that before. And when we did that, we found a total of 14 so far over the course of the mission. So this is all of them zoomed in, and you can see that they all look pretty similar, and all of them were just present in one spin of the spacecraft. But we still, at this point, have no idea what they look. So we started gathering clues. The first thing that we noted is that they are extremely short-lived. So here is a histogram that shows the photon detections as a function of time. See, there's like a big spike at the beginning, and then within just a couple of milliseconds, it's completely disappeared. So really, really short-lived. And then secondly, we find that they are dominated by hydrogen emission. So this is what the spectrum of these bright flashes looks like. So it's the brightness that we're seeing as a function of wavelength. And different molecules have different spectral signatures. So that double peaked feature that you see, that's really indicative of hydrogen emission. And that actually looks really similar to what the auroral emissions look like, because they're also hydrogen dominated. And then the final clue that we have is the location. We find that these bright flashes are happening really high up in Jupiter's atmosphere. And that information is something that we also get from looking at the spectrum. So that left part of the spectrum is really sensitive to absorption in Jupiter's atmosphere. So if the bright flashes were deep down in the atmosphere, it would get, the light from there would be completely absorbed and it would be zero. The fact that it only gets partially absorbed allows us to pinpoint the location and tells us that it's a couple of 100 kilometers above the main cloud decks. So we have this set of clues. Still weren't really sure what it was. So we took to the internet and started reading lots of papers and emailing friends and colleagues who might have some ideas. And what we came up with were transient luminous events. So transient luminous events, or TLEs, are an atmospheric electricity phenomenon that's seen on Earth but had never previously been seen on another planet. They're located really high up in the atmosphere, kind of bright flashes of light, but they're triggered by lightning happening in a thunderstorm down in the main cloud deck. And there's a couple of different types of TLEs, all with fantastic names. So sprites are these kind of like red jellyfish type features, and they're triggered when a lightning strike down at the cloud layer causes a quasi-electrostatic field to be generated really high up in the atmosphere. And then electrons get accelerated, they hit into nitrogen molecules, and it causes red emission. Elves have a kind of similar mechanism, but the lightning strike causes an upward moving electromagnetic pulse, which causes this like diffuse ring-shaped emission. The TLEs are actually very difficult to see on the Earth. So firstly, they're very, very short-lived, just a couple of milliseconds long. And then they're high up from the atmosphere. So if you're on the ground, normally they're completely obstructed from view by the thick clouds of the thunderstorm that's causing them. So really, it's very difficult to see them. And the first people who did report them were actually pilots in World War II, who reported seeing these like weird red flashes up above the clouds, and I don't think anyone really believed them and thought they were just imagining things. And it wasn't until 1989 that a sprite was actually caught on camera for the first time. But when they are caught on camera, it is pretty. So this is a photo that someone took out at the McDonald Observatory in West Texas. So he works up on a mountain, and he saw a thunderstorm was happening down below where he was, so he got out his camera, started recording. And when this bright flash happened, it was so short that he could only just see it by eye, like he kind of thought maybe there was something, but then when he went back through his footage frame by frame, he had this image. It's kind of amazing. And then here's another one from the top of Mauna Kea in Hawaii. And so in this one, you can actually see the lightning down below that's kind of triggering the TLEs, and then there's a sprite, and actually a blue jet as well, which is another type. So TLEs have never been observed on another planet before, but lightning has several times on other planets, including on Jupiter. And theory has suggested that because lightning is there, there should also be TLEs like elves and sprites. Even though there had never been observations before, there had been theoretical studies that had predicted what they should look like. So there were kind of numerical computational codes and lab-based experiments that between them came up with a kind of set of predictions of the spectral shape, the duration, the altitude at which they should happen. And those predictions match up really well with the observations that we made with UVS. It's not a completely sure thing. If we had an observation of one of our TLEs and lightning happening down below at the same time, that would be like a completely certainty. We haven't managed to get that yet, still holding out some hope. But for now, it's a pretty good preliminary detection of the first extraterrestrial transient luminous events. And then, while we were in the middle of writing up that paper, we happened to come across another surprising observation. So we saw another bright flash that once again was only present in one spin of the spacecraft. But this one looks a little bit different to the previous ones. So there's two main differences. The first is the duration. So the TLEs were really short, just a couple of milliseconds long. And this one on the right, which is the new bright flash, it's kind of about 17 milliseconds is that width. It's kind of a Gaussian shape. But actually, that isn't telling us that it lasted 17 milliseconds. 17 milliseconds is exactly how long we'd expect to observe a permanent object if it stayed in place as our UVS field of view sweeps across it. So we know it wasn't permanent because it wasn't there in the following spin 30 seconds later. But maybe it lasted something on the order of seconds rather than milliseconds. And then the other big difference is the spectral shape. So the TLEs had that hydrogen double peak that I was talking about before. But instead, this new bright flash has a kind of smooth spectrum that reminds us of a black body emission, which is the kind of thermal emission that a really hot object gives off. So now we have two different clues for this new bright flash. And what it's consistent with is a meteor impact on Jupiter. And when we kind of measure how bright it was, we think it was a meteor that was maybe like a couple of meters in diameter, so not a huge one. There are meteors hitting Jupiter all the time. It's like a very big planet. It happens a lot, but it's quite hard to actually detect it. We don't see them that often. The last time that a spacecraft observed an impact on Jupiter was actually in 1994 when comet Shoemaker-Levy 9 hit Jupiter. That was a much bigger impact. So this was like a couple of meters across. That was like over a kilometer across. It's a very different scale. And people, because it was so big, people knew in advance that this impact was going to happen. So astronomers gathered at telescopes around the world to see it happen. I was a little too young to be there in person at the time, so I had to Photoshop myself into this picture. But more recently, amateur astronomers here on Earth have got so good, and their telescopes have got so good, that they're actually able to observe impacts these days. And they generally have much better time coverage than the professional observatories. So in the last 10 years or so, I think 7 or 8 different impacts have been recorded by amateurs, and they've been turned into professional scientific publications. And so gathering together all this information from different sources about impacts kind of helps us figure out the overall kind of impact rate on Jupiter, which is really useful because all these different objects hitting Jupiter bring different molecular species and metals to the planet. And so if we really want to understand Jupiter's history, we need to know how its composition has changed with time, and the impacts are a big factor in that. So I was just highlighting 2 of the many studies that have been done with the UVS instrument on the Juno spacecraft. It shows sometimes kind of weird, confusing observations that you don't know how to explain at the beginning can turn into fun science. There's another 3 more years of Juno, so hopefully there will be more surprises to come.
Oh, sorry, yeah.
Check. Thank you, Rohini, again. That's awesome. Thank you. I think you're making our heads spinning. That was an easy one. So if you guys have any questions, about Jupiter, she's the expert. So text any of your questions. I got one coming here, and I'm hoping many more. So the first question is: since Jupiter has a lot of storms, would you expect lots of sprites outside of the auroral regions?
Yeah. So actually one of the things we tried to do to kind of show that it was probably sprites is we looked at the regions on Jupiter that have the most storms, that historically we know likely happens in, and we did show that they happened, our observations were happening more often in those regions than other regions, which we think is a good sign.
Cool. What is your favorite portion of the electromagnetic spectrum? Personal question.
Even though I started with infrared, I have to say I think it's the ultraviolet now. I really enjoy that we count our photons one by one. It's entertaining.
All right, any more questions? If you feel brave enough, you can shout your questions in the air. Questions? Yeah? Yeah, go ahead.
Okay, so you said it's a polar orbit,
Mhm.
right? And so you're primarily studying those auroras. What kind of studying like the middle latitudes with this? Yeah.
So the remote sensing instruments, so like the ultraviolet one that I'm on, and also like there's an infrared camera and visible light ones, they're mostly focused on the poles. That's kind of what they have a really good view. You can do some stuff at the equator, but you're really close in at that point. So you're looking at small scale structure is great then, but kind of getting a bigger global view is harder. But there's loads of other instruments where the kind of having the full orbit is super important. So like there's a gravity instrument that's trying to understand what Jupiter's core is like. And so it's really important for them to measure how the gravitational field varies the whole way around, and so then they can build up a big global picture.
That composite photo of the aurora, we added on the visible light photo Jupiter. Was the relative brightness of the ultraviolet aurora kind of the same, as bright as it looked in the photo, or how bright is the aurora, I guess I'm asking?
Yeah, I guess it's hard to know like, if we could see the ultraviolet, what it would look like. I guess it depends on how sensitive our eyes would be to the ultraviolet. I mean, Jupiter has the most intense aurora in the whole solar system, so it's more intense than the Earth's ones, definitely. It's got the strongest magnetic field, so that comes with it, the strongest aurora.
Well, talking about the aurora, how big is the borealis on Jupiter compared to Earth?
Oh, I have no idea. Do you know?
It's about, I think, twice the size of the Earth, like from one end to the other.
Yeah, that sounds about right. Given that the Great Red Spot is like the kind of size of
The aurora.
the Earth, and then the aurora is like bigger.
Another question, what the hell was the name Sprites and Elves?
It's one of those like hilarious acronyms. I can't remember what it actually stands for, but I think they basically came up with cool names, and then they tried to like come up with something for S and something for P. It's painful.
It's like people discovering the Steve Aurora, and they came up with the acronym later, right?
Yeah.
I think we have the question around here. Yes.
So, I've been watching these for a while, video and stuff here on Earth. Have you looked at the altitudes involved on Jupiter versus Earth, and is there a correlation, or is it completely?
For the elves and the sprites? Yeah, I mean, so they're kind of similar. In both cases, the relevant altitude is kind of how far it is above where the lightning's happening.
Right.
So kind of for Jupiter, lightning happens really kind of far out of the planet, so a couple hundred kilometers above that is kind of equivalent-ish to where it happens on the Earth.
So have we seen any of those events in other wetlands?
No,
No.
not yet. I don't know how easy it would be to see them. Yeah, I guess in theory, I mean, it's hydrogen emissions, so anywhere else that there is strong hydrogen emission, you'll be able to see it, but UV is probably the best bet.
Now a question, how long does it take to communicate with the satellites orbiting Jupiter?
I don't know, what is it?
40-ish minutes,
Yeah,
I
I
think.
don't
40 to
know.
50. I mean, Earth rotates around the sun, so Jupiter is 5 times further than Earth is from the sun. So like if Earth is on the other side, it takes a little longer.
Yeah.
So you have a little bit of variation like that. Yes, and what do we gain? Very philosophical questions from studying these different types of storms on Jupiter.
Just understanding the beauty of the universe better.
That's a beautiful response. Cool. Well, oh yeah, another questions over here?
I was just curious, how do we detect impacts in Jupiter?
Detect what, sorry?
Sorry?
So you said, how do we detect?
Like the impact of the asteroid?
Oh yeah, I mean, so it was like a really bright flash of light that we only saw for 17 milliseconds, but probably lasted a couple of seconds. And it was that black body emission that's like kind of distinctive, that kind of separates it from all the other types of bright flashes that we see. And that's what, when people measure impact on Earth, you kind of get this like black body spectrum. And there aren't very many things that can cause like a really, really hot kind of fireball very briefly. So an impact seemed like a kind of decent guess.
Does it impact the atmosphere?
Oh,
Or
like a really big one, like the Schumacher-Levy 9 one, that changed the atmospheric chemistry for a decent amount of time afterwards. Something like this probably has almost zero impact.
And talking about meteor, who has seen the meteor over San Antonio last 10 days ago? It's a pretty big one. Yeah, you've seen it? Yeah, it was pretty incredible. So, no more questions. Thank you so much, Rohini. Make some noise for Rohini again.
Our next segment is the Astronomy in the News segment, which will be given, as always, by Caleb Gemar, one of the students in the UTSA SWIRI. Oh, I guess I wasn't on. Astronomy in the News, given by Caleb Gemar, student in the UTSA SWIRI Joint Graduate Program, and you can speak more to yourself, but we thank him for his contributions to teaching everybody what's happening, because this is pretty stuff sometimes. So.
Well, thank you. Thanks. All right, hopefully there's not too much feedback. Good. Okay, so astronomy in the news this evening. First and foremost, what is up in the sky right now? So this is your sky chart for around 10 o'clock p.m. for much of the month of August. Do not miss out on scanning the Milky Way with a pair of binoculars. There is a lot to see there, way more than what I can cover in this very brief treatment here, but nonetheless, I've given you the hints that you need. Thank you. Saturn is starting to make its way up in the sky. It is rising over toward the southeast. So if you find a bright star-like object that does not twinkle, that is indeed the planet Saturn. Now, there are more planets that show up as the evening goes on. If you go out about 3 o'clock in the morning, not only will you have Saturn, which will now be almost right in front of you in the sky, you will have Jupiter, which will be extremely bright. You cannot miss it. Sticks out like a sore thumb. And Mars rising over toward the east. And Mars sticks out like a sore thumb as well. It has that very distinct kind of salmon red color. There are a number of meteor showers going on right now, namely the Perseids meteor shower. The Perseids peaks around the middle of the month, but the problem is we have a very bright full moon around that time, and that tends to diminish the ability to see the meteors. So my recommendation, go out over next week or so to be able to see the meteors, because the moon won't be full and you'll actually have a good dark sky. This image is actually an image of a meteor probably from one of these showers, taken by our own in the grad program, at least Jared Schroeder. He's sitting right there. Yeah, he probably is a little shyer, but anyway. So yeah, so that actually is a photograph he took out South Llano River State Park of the of a meteor that went overhead. Really nice photo. So now for what's going on in terms of scientific findings. Well, Lunar Reconnaissance Orbiter, how many folks do we have in the room that work on that program? I know I do a little bit of work with it, yeah. Lunar Reconnaissance Orbiter has taken various images of these little pits on the surface of the moon, and those pits actually serve as these really nice shaded regions, and very recent analysis has showed that the temperature in these shaded regions, unlike the rest of the lunar surface, which is either over a couple hundred degrees Fahrenheit in one direction or 150 below in another direction, is actually a pretty good temperature. It's about roughly 63 degrees Fahrenheit in many of these regions. So rather interesting finding there, and has great potential for future missions to the moon in terms of possible human bases. Now, there's been a number of high-energy astronomy discoveries recently, things dealing with gamma ray bursts, neutron star mergers, things like that. So I'll kind of go through these rather quickly. One, there has been a dormant black hole discovered in the Large Magellanic Cloud. So the Large Magellanic Cloud is one of the satellite galaxies of our own galaxy. You have to go down the southern hemisphere in order to be able to see it, but nonetheless, it is there if you're in the right place to look at it. And within the Large Magellanic Cloud, it was found using data from a number of different telescopic instruments that there is a black hole orbiting around a very bright blue star there in that large Magellanic Cloud, and it is one of few discovered like that that's not a particularly active black hole that has a lot of X-rays being emanated away from it. Nonetheless, there's also a lone gamma ray burst series that has been revealed in data from, again, a number of observatories, but in terms of the initial observations from the Swift Space Observatory, the mystery is, what were these gamma ray bursts associated with? Initial imagery did not reveal any galaxies of any kind there, which would normally be associated with such. However, very deep imagery did find galaxies associated with a number of these bursts. And these actually have been some of the most distant, oldest such observations that have been recorded. In fact, one of these gamma ray bursts from where it clocks in about 10 billion light years away, so a light from about 10 billion years ago. Very, very fascinating. And then this GIF down here shows a very intense radio burst. This is taken by the Atacama Large Millimeter Array of a neutron star merger, and this is the first recorded data like that of such an event over a long period of time. Now, many of you have seen some of the first images posted for the James Webb Space Telescope. I've dedicated this slide to the ones that you may not have seen yet, because let's face it, everyone's seen those first 4 by now. So nonetheless, really beautiful imagery. This one up here is of M74. It really shows the ability of JWST to cut through a lot of the kind of gas and dust and be able to see the fine structure of these galaxies like M74, and certainly a number of very active star-forming regions there, the kind of brighter spots in the galactic arms of 74. The Cartwheel Galaxy, as it's called here, very similar demonstration. This was just released earlier, past few days ago. And then finally, this really great image of Jupiter, kind of an odd-looking image of Jupiter. They've used some rather interesting color combinations for the various filters. But what's really cool about this image is you can actually very faintly see the ring around Jupiter there, which is really, really awesome to be able to see that. And then its moon Europa, right there. Yeah, I knew some of the Europa folks would like that. All right. Now, final reminder, and again, I give this reminder every single time I give this Astronomy in the News talk. Do not forget that there are a couple of very significant solar eclipses coming up down the road. In 2023, we do have an annular eclipse that will be visible over San Antonio. An annular eclipse is where the moon passes in front of the sun, but the moon is not close enough to us to block out the entire disk of the sun, so you get this kind of ring of fire around the shadow of the moon there. You cannot look at this with the unaided eye when it happens. You do have to have the eclipse glasses. And then in 2024, and this is the big deal one, we have a total solar eclipse coming up in 2024. This is kind of when you're in the path of totality. You actually can, when the maximum of the eclipse happens, take a look up at it and see the corona, the outer atmosphere of the sun. So do keep that on your calendars, and thank you very much. That's Astronomy in the News.
Thank you, Caleb. Awesome job. So today I have the immense pleasure to have on stage Michael Velez, so make some noise for him. So Michael Velez was born and raised in sunny South Florida, which explains his love for warm weather and outdoor recreation. Then he received his Bachelor of Art and Physics with a concentration in astronomy from Cornell University, talking about warm and sunny. And he's beginning his 4th year of enrollment in the Southwest Research Institute UTSA Joint Graduate Program in physics, in space physics and instrumentation. Michael also served as a graduate affiliate on the NASA Europa Clipper mission. And his current topic of research include developing a stellar catalog of ultraviolet research, analyzing optical emission of Europa using the Hubble Space Telescope, and constraining molecular hydrogen levels at Europa also using the Hubble Space Telescope. So today, he's going to present us about the stellar occultation work he's been doing at Southwest Research Institute. So make some noise from Michael Velez.
Thank you. Thank you. Thank you. Well, hello, everyone. The word, yeah, I'm getting there. So, you know, the woo, so, you know, we'll just get practice, you know. So my word will be target. So target! Woo! You'll see why. Don't worry. I could have made it occultation, so. And of course, you know, the number is everywhere, you know. All right, here we go. So yeah, stellar occultations, what are they and why do we care? I feel like with any science talk, those are the two questions that everybody really asks themselves, aren't they, right? So I just simplified it, put it in the title. What are they and why do they care? So what are they? So a stellar occultation is effectively when you have a target object passing in front of a background star viewed in inertial space. And that effectively just means with respect to the observer. So what I am seeing is, if I'm staring at this star, so I'll just jump straight to the photo here because it really, I like it. I made it, so I like it. So this is an example of a spacecraft, for example, that you would have orbiting your target. And so as it's orbiting and it's staring in the direction of the star, and it's really far away, so it's, you know, even though intuitively you would think, oh, no, it's far away, so it's just the same direction. And as it's orbiting, the planet looks like it's moving, or the target, I mean, looks like it's moving, and then it'll eventually block the star. The start of it is the ingress, and then, you know, it keeps moving and keeps moving, and then all of a sudden you can see the star again. That's the egress, so start and stop. So that's basically the essence of a stellar occultation. So you know, you have the light being blocked, and importantly, if it has rings, you can imagine, right, the rings are solid or they have material in them, that'll block light as well. And then if it has an atmosphere, you have this interesting effect where the foreground gas will absorb the light, which, you know, photons are coming from the star, and they'll be absorbed by the gas because each gas has its own absorption signature. And that's like a fingerprint of what you're seeing. And you can determine the composition of the atmosphere this way. And if you have good enough data, you can go even further and measure densities. So I've already started to explain why it's important, but that's basically what it is. So you have this star coming in, and you're getting science right off the bat. So there's the picture again. So like I said, it doesn't have to be a spacecraft. You can be on Earth and same thing. So I wanted to give you all a very just intuitive, simplified view. It's not always this perfect of what you would see if you saw this happening. So it's moving, moving, moving. All right, bye-bye. Hello. It's very simple, right? You know, very simple. But why do we care? Why? You know, what's going on here? So I'm going to start by talking about rings. Rings, we all know Saturn has rings. If you don't know Saturn has rings, then sorry. So rings. So my little diagram, you know, you see you have the ring here. And so when the star is going through the ring, you would experience a drop in light. And now this is almost perfect, where your target, you know, would be like a Uranus target. It's on its side. What if it wasn't so perfect? It's a little bit harder because you have to make sure that, you know, the star is going in the right area, but more often than not, you're going to get science out of it because there's a lot of opportunities. And when you think about how distances work, the solar system objects are much, much closer than the stars. So you're going to get something. So here we go. I was setting up rings because in 1977, the first rings for Uranus were discovered using an Earth-based stellar occultation. And this is big because this is really kind of the first non-Saturnian ring, discovery. Because with Saturn, you can, from Earth, if you see it from a telescope, you can see them. Unmistakable, you can see them. But the other gas giants, you really can't, or not with your naked eye. So they use this, our technique. And what we see on the right in this photo is those dips. So you have 1, 2, 3, 4, 5 rings, and they were, very classic science. You just pick a numbering system, a lettering system. This one's a Greek lettering system. So alpha, beta, gamma, delta, and epsilon. And this is the ingress. Remember, I was talking ingress before, and the egress after. They flipped it so that you can do a direct comparison, but you see it on both sides, and so that's indicative that you're looking at rings. And then later on, in 1989, Saturn's rings, which, like I said, you can see them, but they were much more well-defined by these stellar occultations, because you can see exactly when the light is coming and going, or disappearing and reappearing. So you can really start studying these things, and really powerful. And then I think this is really cool. In 2014, 2 rings around Chariklo, a centaur, were discovered by an Earth-based stellar occultation. Now, a centaur is an object that exists between Jupiter and Neptune. And they're really small objects. Now, this one is the largest of the centaurs, but still, they're not these terribly big things, and when you think about where we are on Earth and how far away the outer planets are, to not only see this thing, but to actually get ring signatures, really, really powerful. This is why stellar occultations are important. So then, I've talked a little bit about Earth-based observations. So with spacecrafts, if you take the spacecraft and you go at or near the system, you can do much more detailed analysis, because the obvious thing when you're at the target, you are taking pictures of it. You can see it with your eye. If you have a camera on your spacecraft, you can see it. But you gain so much more by doing stellar occultations, and Cassini did this at Saturn. Not only did it take these beautiful photos, go on Google, some of the photos are beyond breathtaking, but it also used hundreds of stellar occultations to really constrain what was there, abundances, the clumpings of everything, and we learned a lot about the rings of Saturn because of these occultations at the environment. And, to keep along that path, pictures just continue to aid occultation findings. Voyager 2 visited Uranus and Neptune. Like I said, Uranus, we had already discovered the rings. Neptune, there had been discoveries. It had been a little floppy because Neptune, A, is farther away, and B, its orientation at the time led to less stellar occultation opportunities than Uranus. So when Voyager 2 got there, it confirmed, it took pictures of the rings and said, yes, the stellar occultations got it right. They found the rings. And in Neptune, something very interesting happened. When earlier occultations said, one of them was like, oh, this kind of looks like a ring, but not really. It was only on one side, and then it disappeared, so we don't know what it is. So Voyager gets there, and it takes pictures of everything, and they found that they had accidentally stumbled upon a moon during this stellar occultation. The probability of that, I don't have to tell you, is beyond slim. And because, once again, a ring is all around. A moon is in one place at one time. And Neptune moon, this one is quite small. This one, Larissa, is the name. And so, you know, not a ring, but just goes to show how cool and how powerful this is. So today, rings are continuously being discovered around some of the smallest objects, even Kuiper Belt objects, which are objects that are beyond Neptune, so Pluto and beyond. And we're finding rings around these tiny, far things using this technique from Earth. So that's, you know, just think about that. That's amazing. So why, number two, why is it important? Astrometry. Astrometry basically is when you have, is when you want to measure how big something is. So what you'll do is you'll, the minute the star is disappearing behind the target, okay, good. Making sure. You start a clock, proverbial clock. And then the minute you can see the star come out the other side, you stop the clock. And you know how fast you're going, or you know, if you're a spacecraft, you know how fast the spacecraft is going, and if you're on Earth, you know how fast the object is moving. And so, you know, velocity equals distance over time. You can work your way back and figure out exactly what that distance is. And this has really been done for, like I talked about, the smaller objects in the solar system. We've been able to determine their size and even shape. And for larger objects, you can go beyond that and fine-tune their sizes and look for features on it. You know, if you know how the radius of a large planet, what if it has mountains or ridges or something, then you would see that on a stellar occultation, because, you know, they're not smooth. Nothing is really smooth. That's rocky. And so the asteroids that have been, one of the most notable asteroids that has been measured like this was Pallas, and it was a while ago. And so same thing, you know, you have this really tiny object, and, you know, cameras have pixels. And pixels are really, you know, when you look at a small object, 1 pixel, you know how big your pixel is as far as resolution. You know, you can say 1 pixel is 10 kilometers. But when you're dealing with a small object, it's going to be 1 pixel, whether it's 10 kilometers or 5 kilometers. So when you have stellar occultation, you can go beyond that because you have that light timing. So it helped us with asteroids. And then I talked about those far Kuiper Belt objects. On the right here is a light curve for KBO 55636, just a naming convention for Kuiper Belt objects. And you see here what they do, right? The light's coming from the star, it's gone, and then it comes back. You have that time, you have that speed, you find the size. And then Eris, Eris asteroid, or I'm sorry, dwarf planet, Eris. And then Aerokoth, one of the cooler objects in our solar system, which was actually photographed by New Horizons. But before New Horizons got there, we already kind of had ideas on shape, size and shape, because of these stellar occultations. So once again, this is ground-based observations helping future space-based observations and maximizing science. All right, last but not least, and probably my most favorite, atmosphere, because that's what I do. So this one is very simple, right? You know, it's coming through the atmosphere. I talked about the light is being absorbed from the atmosphere by specific gases, and what you'll get very cool curves, which we will see. So do this to really show you how long occultations have been going on. Technically, they've been going on forever, right? The universe does them, right? Like, you know, if you look in one direction, you can see them. And some of them, you know, you could feasibly see with the naked eye, but it would have to be a really bright star. And this kind of happened with Venus and Regulus in 1959, and then earlier Jupiter had an occultation in 1952. And they turned the telescopes to look at these, but the technology just wasn't there. These telescopes, they were good, but they weren't that good to get real atmospheric science. So we had to wait a little bit. And then in the 70s, they sent satellites off to orbit Earth, and what they did was they turned it towards Earth, and did stellar occultations of the Earth's atmosphere from Earth orbit. So we learned about our own planet using this technique. And then perhaps one of the coolest things was Pluto, when its atmosphere was discovered by a stellar occultation during the year 1988. And once again, remember, Pluto is far, Pluto is small, so we are detecting its atmosphere. And this was it right here. This is the signal. And I like this photo because it shows, we talked a little bit about astrometry and stuff, so the light goes away. If it had no atmosphere, it would just go straight up, right? The light would be gone, right, and straight down. But when you have an atmosphere, you start having the dips on the edges here because you have the light starting to be absorbed. So that tells you, at the very least, you have an atmosphere. And then you can go and use wavelengths to find what, which was done by New Horizons back in 2015 when it did its famous Pluto flyby, and it sent those beautiful photos back, including the heart. A stellar occultation was done not long after the flyby by the ALICE instrument, which was a UVS instrument, because UV is just amazing. And this is an example of one of the plots. And what I really want you to take away from this is you see these colored lines where they match this red line, and that's statistical fitting. And those colored lines correspond to gases in the atmosphere. So when you fit it to that curve, you're figuring out what's in this atmosphere and how much is in it. And that's what was done, and that's how we learned all about Pluto's atmosphere all these years later. So really, groundbreaking foundational stuff. And as far as the rest of the solar system, every planet in the outer solar system has been probed in this manner. And a lot of other targets have been as well, moons of these planets. Titan's very interesting. It's got a very thick atmosphere, so it's a great candidate for occultations, and Cassini did those as well. So you can learn a lot from these measurements, and I hinted at it about I like atmospheres because why do I care? Why am I up here giving you this talk? Because well, the Europa Clipper mission, which I'm very fortunate to be an affiliate of, will be launching in just a few years, actually, in 2024, October. And so it's going to explore Jupiter's second innermost Galilean moon, Europa. And once again, UV love. It has a UV instrument on board called Europa UVS. And it's going to perform stellar occultations that are going to do astrometric measurements and atmospheric observations. And on the left here is an example plot showing possible occultations. So the green would be the start of an occultation, the red would be the end, and then this light blue line, you see they're connecting the dots. That's representing, just what terrain it would cut through. So, if you had all those occultations performed on this target of Europa, then you would learn at each of these sites exactly what's, what's going on with good enough resolution. And then with the atmosphere, this is one of my favorite plots because, once again, I made it. The black line is the black body curve of a star. We talked about black body curves. And once you have the light being occulted at the specific wavelengths. So I'll point you to, right here. You can see it kind of real well. And then you see it better down here. This is what we call a transmission curve, which is basically you take the occulted light, the light that's being drained away, and divide it by the original light, and you get a ratio from 0 to 1. And you see that beautiful dip. That's what you want to see. That's where the science is. And this right here, this beautiful dip, that would represent oxygen, molecular oxygen. And that's one of the many things that we're going to be looking for at Europa, because it's got a big ocean underneath the surface, and it could be habitable. So the more we study these elements and compounds, we can learn about its habitability. This science is going to be, really, really exciting and produce hopefully some amazing results. Unfortunately, gotta wait. It launches in 24. It's not gonna get there until the 2030s. So, have a coffee. But yeah. So that's it. Yeah. I hope. Yeah. Thank you.
Thank you, Michael. Thank you. Great talk. Awesome. Thank you. Thank you. If you guys have any questions, text your questions. I got a bunch coming here. First one, what would you say is the most exciting discovery with stellar occultation?
The most exciting? Well, it's tough to say because, I'm biased, and I like I said, I really like the atmosphere. So I think, I'll say it. Pluto's atmosphere. I think that's one of the most exciting ones, just because of, like I said, how far it is, and also you think about this little object having an atmosphere, and we learn a lot about our own solar system, and that teaches us about other solar systems as well. And in 1989 when they did this, exoplanets were an idea. We thought they existed, and today we know not only do they exist, but they exist in multitudes. And by doing this research, we learn more. By learning more about our solar system, we learn more about what can exist in other solar systems. And so I think that is really important when trying to think about that.
All right, I got some Pluto questions too.
Okay.
The dreaded question. Pluto has an atmosphere, so it's definitely has mass. So it's a planet or not?
Titan has an atmosphere, and it has a mass. Goes around Saturn. So, it's a moon. Just because something has an atmosphere and a mass, I know it goes around the sun, but, Pluto deserves love, right? It gave us love. It has the heart on it. It gave us love. But it's, I think it is what it is. We just got to keep researching it because it's an amazing object. We should treat Pluto as if it was a planet. And thanks to New Horizons, we kind of did. Think about it. Uranus and Neptune, only explored once by an old, Voyager was great, but it was old. And New Horizons was a groundbreaking, state-of-the-art equipment. And we have a lot better knowledge, I think, of Pluto and Charon as a result than even planets. So
yeah. Something different. What can be studied with stellar occultation of the moon, of our moon, I guess?
Of our moon. Well, the moon has a very, very thin atmosphere. In fact, I wouldn't call it an atmosphere. The term we use for things like that is exosphere, because it really is just not much there. So you could learn a little bit about that. Once again, you could do astrometry, you can look for craters, but the moon is so well defined. We've been there, we have so many pictures, the LRO, you know, that to me, the stellar occultation on the moon kind of it wouldn't be a moot point. There's always more stuff to learn, but, you know, let's focus on other stuff, you know. Spread the love.
Another question: what would be your most exciting? What are you most excited about in terms of stellar occultation on Europa?
So yeah, like I talked about talked about the oxygen band there, but the most exciting thing is that I talked about this ocean. So Europa is. Let me go back a little bit also. Enceladus, around Saturn, similar-ish moon. Icy shell, ocean underneath. When Cassini went, it found these gorgeous plumes, gorgeous, ejecting water from the ocean. Europa has been found to maybe have these plumes as well, but those, you know, Cassini was actually there. These observations were made by Hubble all the way over here. So it's really kind of one of those things where if you talk to one person, they'll say, yes, there's plumes. And you talk to another person, they'll be like, I'm not sure about that. So with this Europa Clipper, we're really trying to, I hope that we can answer, yes, there's plumes. And an occultation would help with that because you would see water, you would see, you know, not only water, you would see a lot of water. And I think having an occultation through a plume would be the best thing in the world for that mission. So that's what I'm most excited about.
Cool. Yeah, I'm really excited about that too. Can this technique, so stellar occultation, be used to measure distance to the object?
Distance to the object?
Yes.
I'm trying to think. I don't really think so, because distances to objects are we use different techniques. You know, one of them is parallax. When it's close enough, I don't think so.
Okay. And maybe the last question: any thoughts on planetary transitions of a star, similar to occultation, but the other way around?
Say that again?
Any thoughts on planetary transiting over distant stars?
Oh. Okay, so like I talked about exoplanets. So yeah, I think one of the things I did forget to mention, so occultations sometimes get a little bit confused with transits. And it's basically a matter of which one is bigger, the foreground object or the background object. So when the foreground object is bigger and the background object is smaller, it's an occultation because you're completely blocking the light of that background object. When the background object is bigger than the foreground object, it's a transit because, yeah, you're blocking some light, but you can still see the whole background object. So exoplanets, one of the discovery techniques is this transit method, which is very similar, but the dip in the light curve isn't total. It's only as much as the size of the transiting object.
Cool. Yeah, that's a great explanation. Thank you so much again. Make some noise for Michael Velez. So before we take a short break for the trivia, so again, we have a lot of great stuff to win tonight at the trivia, and we'll be distributing during the break, 5 minutes break, this answer sheets. And the rules is that if you have a PhD or if you're about to have a PhD, you're working towards it, you are not allowed to play. I'm sorry.
Yes. You can get a sheet. We'll give you a sheet, and you can write it down, but you can't give it back to me when I collect them.
Yeah. And then before we start the trivia, I just want to say let's give it up both again for Rohini and for Michael for their fantastic talks today. And I don't think any of them are in here, but a big round of applause for the staff here at Blue Star. Don't forget to tip your staff. Woo. And yeah, let's play some trivia.
All right. The big thing, so as always, I always say this, that we'll get new pens and markers, but we're limited on our pens and markers. So if you have pens or markers on you, please use them. Raise your hand if you need one, pens and markers, and I'll come around. Thank you. The highlight, all three winners, top three, will get a 2022 Night Sky Almanac. And then the top two will get this very nice Blue Star cup. Thank you to Blue Star for providing them, and happy 25 years. That's commemorating cup. So it's old as I am.
Put all the answer slides.
Oh, the slide after? Yeah. Okay. Awesome. I did, and I looked like Christine did too, so I think we should be good. All right, here we go. Question 2. How many planets in our very solar system have rings? And of course, I've given you one right there, you know. I'm very generous tonight. A2, B3, C4, D5, and E6. How many planets in the solar system have rings? All right, question 3. The Juno Mission was named after which mythological figure that was able to peer through Jupiter's cloudy disguise? Very apt. A, Jupiter's mistress, an Olympian priestess. B, the god of the underworld. C, Jupiter's nemesis, his father. D, Jupiter's jealous wife. Or E, the goddess of war. This one's an interesting one. I like this one. If you're good at Greek mythology, then, I mean, you know, congratulations. Give you the poster. All right, everybody good with this one? All right, we're moving on to question 4. Okay, rather than occultation, what is the term for when a star does not get blocked completely by the target object, but rather gets near it for science to still be possible? So to TLDR this, remember occultation, it blocks the light. So the light doesn't get blocked with the star. The star kind of goes by very close to the planet or moon or whatever it is, and you can still have absorption in the atmosphere. So our options are A, transit, B, occultation, C, occlusion, D, apulse, E, skimming, or F, close but no cigar. Question 5, which of Jupiter's moons orbits closest to the planet? So which is the closest moon to Jupiter? Is it A, Europa, B, Metis, C, Enceladus, D, Io, or E, Amalthea? Which of Jupiter's moons orbits closest to it? All right, everybody good? All right, last question, question 6. Jupiter's infamous Great Red Spot is a large storm in Jupiter's atmosphere. The lesser-known Great Blue Spot is A, an intense patch of magnetic field, B, a similar storm in the bluer section of Jupiter's atmosphere. I'm sorry. Oh, that's giving it away. C, a large ice storm. D, a visual feature named by the Democratic Party. Or E, the effect of the Great Red Spot being blue shifted, i.e. moving toward Earth. The infamous Great Red Spot, large storm, lesser known Great Blue Spot is what? That concludes all of our questions. However, as usual, we have our bonus. Oh, go back. You good? You good? Everybody good? Everybody good? All right. We have our bonus question of the evening. This one is not multiple choice, so, you know, if you want to run out the door, go ahead. we have audio on this one, so that Vincent's trying to get that set up, but I will read it first. So how was this sound, air quotes, of Juno passing by Ganymede acquired? Wait. There we go. Wow, I could listen to that all day. Sounds like a tea kettle. But nonetheless, it is very cool because it came from, wait. Yep. So remember, just a refresher, the question, how was this sound of Juno passing by Ganymede acquired? So, there's not a lot of space there, so don't write on the answer sheet. So don't write, an essay. Just a very simple answer. If you write an essay, I'll just throw it out. All right, everyone. Thank you for your trivia. We have our winners. But first, the answers. This first question, I was very pleased with how many people got it right. So thank you for listening. Which was, of course, the Venus occultation. The answer is Regulus. Woo! All right, question 2 was about how many planets in our solar system have rings, and the answer to that is 4. That is all the outer planets, Jupiter, Saturn, Uranus, and Neptune. They all have rings. And like I talked about, even non-planets have rings. There's rings everywhere. Number 3 was the question about Juno. And why, who was Juno? Juno was the jealous wife. Yep.
Well, I might add something about that. The mission Juno is designed to actually look through the clouds of Jupiter to investigate the interior of Jupiter. Kind of like what Juno, so Jupiter's wife, did to look through the cloud, to look at him cheating on her on Earth. So Juno is kind of a wink to what happened in the mythology. So it's funny.
Very cool. Yeah, I love Greek mythology. Is so fun. All right, question 4, which was about the. This one tripped a lot of people up. This was about the one that goes by, but it's not an occultation. It is called an apulse. An apulse. Yep. It's actually a general term referring to an object's really close approach to another object, and so that's why it's used in science when we can't call it an occultation, like I said, because it's not going behind our target, but it is giving us measurable science. So, shall we continue? So 5 was about. 5 was about. Oh, that's right. The closest moon to Jupiter. And this one, you asked me a few years ago, I'd say, oh, of course it's Io. But that's the closest Galilean moon to Jupiter. The closest moon to Jupiter is Metis.
Yeah, that's a family picture of, I think Metis is on the right, Amalthea in the center, and then the third one, I can't remember the name, but... Yeah, that's this little guy.
He counts. That's a moon.
It's
That's a
about
moon.
20 miles across, I think, 20 by 20 by something. So it's a small little piece of rocks. But it's still a moon.
Exactly. All right. The last question was about the great blue spot, the blue spot, and the answer to that one was an intense patch of magnetic field. Yep. Although, you know, props to one of our trivia helpers, Christine Ray, for these answer choices, for giving us all a laugh. So let's she's not here tonight, but she helped out. A round of applause to Christine for helping us. Yes. All right, the bonus, the all-important bonus. We all heard that fun sound, and we asked you what it was. It was about Ganymede, and the answer is the scientists converted radio waves measured by Juno's WAVES instrument into audio waves after the spacecraft closest approach with Ganymede. So that's radio waves. That's what's emitting from Ganymede. So that's pretty darn cool. You can go on Google, online, and you can search the sound of many, many solar systems objects. Every object has a sound because they all have radio waves of some sort. So these are online, and some of them sound very interesting, like what we heard. So I recommend looking at that if you want, you know, a new studying soundtrack. You know, why not? All right.
So we have 3 winners. We have, we're going to start with the number 3. And the team name is? I'll let you.
Robert's Girls. Come on up.
I love it. Which one is the number 3?
This one.
This
You
one?
get a Night Sky Almanac. Woohoo! Thanks to Robert. And this wonderful MMS Magnetosphere Multi-Scale Mission poster, which I'll give you a sneak preview. Our next AOT will feature a talk about this, so come learn about it at our next AOT.
We'll put it in the library.
Woo! There you go. Woo! Congratulations. Congrats.
Next we have Charles and Company.
Woo!
Again, you have this. Wait, is this number 2?
No, it's this one.
Okay.
The Night Sky Almanac, as usual. The Blue Star Cup, and there's something inside, and a poster about. It's the International Year of Glass. So, it's a glass poster. Very cool, very interesting.
And the winner is?
All right, the number 1 prize, which let's draw it out. I love drawing it out. The Night Sky Almanac once again.
Another cap from Blue Star. And
Cap.
again, thank you, Blue Star, for donating this. That's awesome.
A NASA LRO 10 anniversary poster, which it looks so small, right? No, this thing is huge, okay? So whoever's taking it, I hope you have room. And then a beautiful poster also from the conference, a very pretty. It's a women in optics poster because it features Sunita Williams, astronaut Sunita Williams, who studied in Florida. And it's a very cool poster, and she's a very cool lady, so look her up too. It's very, very cool.
But I think what people want to know is, what's the name of the winner?
Oh, yes.
What's the team name?
Ethan? Ethan.
Meg, Ethan,
Wait.
Chapel.
Okay, them. Them.
All right.
Okay.
Congrats. Awesome job. So that's for you. Thank you.
Here's all your...
All right. Thank you, everybody. Again, make some noise for everybody tonight, for people who played, for the speakers.
Yes, thank you, of course, to the Southwest Research Institute. They help us put this on. Everybody involved works, or most everybody involved is at the Southwest Research Institute, and of course we have our wonderful tech crew. Thanks
Yeah.
to the tech
I
crew.
think we forgot to really pay a tribute to you guys. Thank you, Adam. Thank you, Brian. Thank you, guys, for the streaming, the video, for making this available online. Thank you so much again for the support. Yeah, that's really awesome.
And a big thanks again to Blue Star and to the staff here. Don't forget to tip your staff. Thank you all. A big thanks to Robert Reeves, who was our speaker last time, that donated the almanacs for the winners tonight.
Thank you, Robert. Yeah.
And a big thank you to all of you for coming out and enjoying some space talks and having some drinks, and we'll hope to see you next month. Thank you all. See you in July.